Welcome to Spring LIB.
Okay, in this problem we have some accelerated electrons that they're accelerated by a potential difference of 5,500 volts. Then they pass into a region into two parallel plates that are 6.5 centimeters long, 1.3 centimeters apart. And we are asked to find the angle of deflection for these electrons after they pass through these plates. So to start, we can look at the horizontal direction. We can figure out how fast these electrons are going. That is, the initial potential energy must be equal to their final kinetic energy. From this, we can get the potential energy due to simple voltage. We know delta V. We know the charge. We can set that equal to its kinetic energy in the x direction. And we can, from there, we also can have we know that time that it passes through the plates is simply equal to the delta x, the distance of the plate, over the x velocity of the electron. Cool. So now we can take a look and look at the forces on this electron as it's being deflected. So the force is electrostatic. It's Q times the electric field in the y direction due to these parallel plates. And it's also equal to the mass times acceleration of that electron. We can express acceleration as final y velocity minus initial y velocity, so just a delta v in the y direction over t, assuming that it's uniform. That's a linear acceleration, which it is. Thus, velocity in the y direction will be q times electric field in the y direction times t over m. We can simplify that further as q y electric field, the distance that travels across the plate, over mass times x velocity. So now we can take a look. We can arrive at an expression for the angle by using the tangent of theta, relating it to the ratio of its y and x velocity, these electrons. We can replace the y velocity with q electric field in the y direction, delta x, the expression that we derived earlier. And of course, this will all be over our Vx. We can simplify this down a little bit. Q, E field, delta x, and Vx squared. And we can express Vx in terms of the total V. So we have Q Ey delta x over 2Q V. This is using the potential. Oh, and this is not the velocity. This is the potential, big V. We use that expression at the very start by relating its initial potential energy to its final kinetic energy. So now we can replace velocity by some other quantities that we actually know. And we can, at this point, arrive at an answer. So we have about 0.1138 for tangent of theta. Thus, theta is the inverse tangent of that number, 1138, which will yield an angle of deflection of about 6.5 degrees. And that's it. We used conservation of energy, we used a little bit of forces, and a bit of trig to arrive at the answer. And that's it.